Hi, welcome back to this video series on Diffie-Hellman key exchange and in particular discussions on parameter selection. We have been talking about how different implementations handle the DH parameters like the group generator and how do they check whether it's a safe prime or is it a good generator and so on. Today I'm going to talk about one implementation specific detail actually. I saw this in OpenSSL as well as in Boring SSL source code. In fact, my friend also shared this with me. They check whether a given prime is a safe prime first, and then they check whether is G 2, 3, or 5 a good generator, right? We have seen how to do that in the past videos. We used very simple tricks like this one. For example, we saw if G power Q is equal to 1 mod P, right? We concluded that G generates a subgroup of order Q, right? In the context of the safe prime. If we assume P is equal to 2Q plus 1, both P and Q are primes. If this property is true, then we know G generates a subgroup of order Q. But this requires obviously using an exponent operation, right? We are trying to raise G to the power Q. There are special cases. For example, what if G is 2, okay, or 3 or 5? We don't have to do this G power Q. Remember, if P is a 2048-bit number, Q is almost same as 2048. I mean, it will be 2047 or something like that. So we will have a very large exponent. Therefore, it will be nice to check in a much faster way by using some of the techniques that are described here. But what is not clear though is that what is the reason that, for example, in order to check 2 is a generator for the group, it is enough to check P mod 24 is equal to 11. Let me be clear. We are here talking about generator of the group, not the generator of the subgroup. For some reason, OpenSSL and also a couple of other libraries, they select the group to be safe prime group, but they don't work in the subgroup. They work in the main group, the group of order P minus 1. For example, I saw here in OpenSSL, there is a method called, or a function called DH built-in gen parameters. Let me pull the method that is of interest for us. So here is a lot of text. Let me quickly read through this. What they're saying is that we generate DH parameters as follows. They generate a prime Q, and then they generate a prime P. If P is equal to Q plus 1, they conclude we have a good safe prime, right? That's true. And then for the generator case, they check whether G power Q is congruent to 1 mod P. That's basically what I talked about in my previous segments. So this portion of the comment is basically checking whether G generates a subgroup, right? That's basically what they're generating, what they're checking. However, they are here checking whether G is generating the entire group, not just the subgroup. That's what they're trying to do here, right? We talked about this condition in my previous segment, that for an element to be a generator, if we know the prime factors of the group's order, we can easily check it. In the case of safe prime, it's easy. The safe prime cannot have subgroups other than subgroups of order 2 and a Q, right? Obviously, I'm eliminating the subgroup of order 1. Therefore, it's easy to check whether G equal to 2 or for that matter, any G is actually a generator of the entire group. Very easy, okay? That's not what I'm going to talk about now. I'm going to talk about the part that is discussed here. For P equal to 2, they say, okay, it is enough to check whether P mod 24 equal to 11. Okay, so my friend asked me an interesting question. Why is this P mod 24 equal to 11 is enough to conclude that G is generator of the entire group? Okay, so it turned out that that question can be answered in a systematic way. First, let me show you some of the properties of quadratic reciprocity rather. So quadratic reciprocity and quadratic residues were studied by lots of famous mathematicians like Euler, Fermat, and Gauss, Legendre, and so on. They investigated the equation of this format, right? X squared is congruent to A mod P. In general, they studied that. So in this case, X squared is congruent to 2 mod P. So it turned out that this is kind of a beautiful result. If X squared is congruent to 2 mod P, then we can be sure that P is congruent to 1 or plus 1 or minus 1 mod 8. If P is congruent to plus or minus 1 mod 8, we can conclude that X squared is equal to 2 mod P. What it means is that if we have a P and we find that P is congruent to plus or minus 1 mod 8, we can conclude that 2 must be a quadratic residue, because you can find an X. The theorem doesn't tell you what the X is, but it does tell you that 2 can be expressed as power of 2. Okay, that's what it's saying. If 2 can be expressed as power of 2, we know that 2 is actually what is 2 then? 2 will generate a subgroup, right? So what is the subgroup? That will be the subgroup of order Q in the case of prime, safe prime, right? That's we have learned it several times. So what is this theorem telling us? So what we can do is we can take a P from say from an R of C and apply this theorem, right? For example, let me take the R of C 7919. Here is my P. Here this whole thing is P, of course, and here is my generator. In this case, let me make sure you are on the same page with me. In this case, G equal to 2 is a generator of this subgroup of order Q. Okay, it's not going to generate the subgroup of order P minus 1. It's going to generate the subgroup of order Q. Okay, so that's something we have seen it several times, but we can use now this theorem to check that. Okay, what does it mean by using the theorem to check? If the theorem says, what can I say? If the theorem says P is congruent to plus or minus 1 mod 8, we can be sure that our 2 is a quadratic residue, right? Okay, let's check that. If 2 is a quadratic residue, it must be generating a subgroup of order Q. That's something we have been seeing for quite some time. So let's check that. Let's go to the Python terminal, right? Let me get my R of C document opened, and here's my P, right? Okay, so I'm going to copy this P and I'm going to paste it here. This is my Python interface. So now I'm going to just do P mod 8. Okay, what does the theorem say? If P mod 8 is plus or minus 1, we know for sure the number 2 is a quadratic residue. So what is 7? 7 is nothing but minus 1 in mod 8. Okay, 7 and minus 1 are same. So what it means is that our number prime P satisfied this theorem, this part of the theorem. It says P is congruent to plus or minus 1 mod 8, right? P is, in our case, congruent to plus or minus mod 8. That means 2 is indeed a quadratic residue, right? If 2 is a quadratic residue, we know for sure 2 will generate a subgroup of order Q. So we are done. Okay, we are done in the sense we confirmed that this 2 will definitely generate a subgroup of order Q. Okay, so now let's get back to the OpenSSL context. Okay, so OpenSSL is interested in not checking whether 2 is a generator of a subgroup, but they're interested in checking 2 generates this entire ZP star group. Okay, so how do we check that part? So for that purpose, I actually went ahead and generated some primes using the OpenSSL utility. Like, for example, I will show you OpenSSL has command line utilities to generate Diffie-Hellman parameters. So I went ahead and generated some primes. It took me a couple of minutes, so I thought I will first do it, and then I will just copy and paste the primes. So what I'm going to show you today is, here is my prime P, which I got from OpenSSL, and it does satisfy the safe condition. So as you can see, it does print safe. But it is also interesting to see that if I do G power Q, G is 2 in my case, G power Q mod P, it was actually not satisfying it. That means G equal to 2 is actually not generating the subgroup of order Q, although we are working with safe prime. But what kind of test can we confirm without doing this? Without doing this, can we use the theorem to confirm that that actually G equal to 2 is in fact not a quadratic residue? Okay, let's do that. So we copy and paste this, right? And we check whether the modulus of this with 8 is plus or minus 1. So how do we do that? Very quickly, we can do this here. We paste the prime and we print P mod 8. Okay, P mod 8 is 3, which is not plus or minus 1. Therefore, the theorem is saying that if P is not plus or minus 1 mod 8, then your number 2 cannot have a solution to this equation, meaning 2 cannot be expressed as power of 2, the power of some x, okay? And 2 is not a quadratic residue. Okay, so when 2 is not a quadratic residue, what can you conclude? By the way, P is prime. Therefore, we can conclude that number 2 must be generating the entire group. So they're basically generating a generator G equal to 2, which is they're using G equal to 2 as a generator to generate the entire group, right? This argument, this logic that I just mentioned is only true if P is a safe prime. Okay, I'm going to toward the end of this session, I will show you that if the prime P is not a safe prime, then if this condition x square is not congruent to 2 mod P, cannot tell you whether the number 2 is a generator or not. Okay, so we can talk about that later. But at this point, I would like to tell you that if P is a safe prime, and if this condition is violated, meaning if this condition is violated, B is not congruent to 1 mod 8, then we know for sure that the number 2 is actually a generator of the entire group because it's not a quadratic residue. Okay, so now let's go back to the 24 question, number 24. Where is this 24 coming from? So what we can do is we can do a simple trick here. So I will just write it here very quickly. All we have to do is just to rewrite the theorem. We know for sure the theorem says if your number is 1 mod 8 or minus 1 means 7, right? 7 mod 8. Okay, so what can you say that if your prime number satisfies this property, it implies, okay, in the context of safe prime, what does it imply? It implies 2 is a quadratic residue, right? We checked that part. Okay, so this is clear. So what does it mean by P? Let's take the first part. P equal to, let's consider this case, the G is equal to 2, and they are saying it is enough to test P mod, it is enough to test P is equal to 11 mod 24, right? That's what they're saying. So what is P equal to 11 mod 24? How can we rewrite this? We can rewrite this as 24 times some k, some integer k plus 11. That's basically the definition of mod. Okay, so how can I rewrite this? I can rewrite this as something like this. I can rewrite this as let's say 8 times 3k, right? So maybe I should write it like this: 24k plus 8 plus 3, which is 8 times 3k plus 1 plus 3, right? So essentially I have my P is in this format, plus 3. Okay, now if I apply mod, well, what is the mod notation of this? This means P is equal to 3 mod 8, right? Essentially that's what it means. If P is equal to 3 mod 8, what can I say? Now if we go back and apply the theorem, obviously 3 mod 8 is not the same as 1 or 7 mod 8. Therefore, it implies 2 is not a QR, right? When 2 is not a QR, what can we conclude? That means 2 is not going to generate a subgroup of order Q, right? 2 is not going to generate a subgroup of order Q. Okay, so what kind of group will 2 generate then? Remember, we are in the safe prime context. Therefore, 2 must be generating the entire group P of order P minus 1, right? That's basically it. So by just testing the fact that P is congruent to 11 mod 24, or equivalently P is congruent to 1 mod 8 or 7 mod 8, we can conclude something about whether number 2 is a quadratic residue or not quadratic residue. That's basically what this DH check function is actually doing. They don't use the exponent. They simply use this little fancy trick from math, right? The quadratic reciprocity supplement that helps us to conclude this. Okay, so one final thing before we wrap it up very quickly is that let me show you what happens if we do P mod 8 in general. Okay, what are the possible values you will get when you do P mod 8? A couple of possibilities. Okay, P mod 8, of course, when you divide a number by 8, what are the possible reminders? It can be all the way from 0 to 7. You can't get a 0, of course. If you get a 0 as a reminder, it means your prime P is a multiple of 8. P cannot be, P is a prime, so it cannot be a multiple of 8. So P mod 8 has to be either, what are the possibilities? It can be 1. Can it be 2? Well, it can't be 2. If it is 2, what you're saying is 8 times some number plus 2, which is an even number. So P is obviously not an even number. So 2 can't be the remainder. We can have 3. We can't have 4. We can have 5 and 7. So these are the possible values P mod 8 can have. Okay, can have. So let's walk through one by one. So what happens if you have the value P mod 8 as 1 or 7? Okay, so we looked at the theorem, right? If P mod is 1 or 7, they call it plus or minus 1, right? Then X is, then we have learned that G equal to 2 is a quadratic residue. Okay, that's for sure. We learned that. Okay, what is interesting though is that let's consider the other case. Okay, can we have Q to be 5? Can we have P mod 8 to be 5? Not Q. Can we have P mod 8 to be 5? It turned out that we can't. Okay, how do we check that? So let's check it here like this. If P mod 8 is equal to, say, 5, what can you say about it? If P mod 8 is equal to 5, what it means is that your P must be 8 times K plus 5, right? Okay, so we can just reorganize it a little bit like this, plus 4 plus 1, which is nothing but, if I take my 2 as a common, what do I get? I get 4K plus 2 plus 1. Okay, obviously this is not a safe prime because 4K plus 2 is an even number, so this cannot be a safe prime. Therefore, P is equal to 5 mod 8 is impossible in the context of a safe prime. Okay, so this is not possible. Okay, P equal to 5 mod 8 is not possible if P is a safe prime. Okay, so all you have to do is check whether P is equal to 1 mod 8 or P equal to 7 mod 8 to conclude whether number 2 is a quadratic residue or not. Okay, that's basically what the core idea is, used by OpenSSL and Boring SSL and other libraries. Okay, so there is one interesting thing in the end it is worth to highlight. If the number P is not a safe prime, okay, if the number that you're working with is not a safe prime, you need to be more careful to conclude anything. So if, for example, your number is, say, 43, okay, what if we take number P equal to 43? Okay, let me run this quickly. So I'm going to run the Python code that will generate my groups. So I'm going to do the quadratic residues generator for 43. We know 43 is a cyclic group. Okay, and what can you say about 43 in terms of the modulus? Okay, print 43 mod 8. Okay, which is 3. So obviously this tells us that number 2 cannot be a quadratic residue, right? Because in order for this to have a quadratic residue, you must have a remainder 1 or 7, but remainder here is 3. Therefore, 2 is not a quadratic residue. So, but can we conclude now 2 is a generator of the subgroup? Well, we can check it here. 2. Can we conclude that 2 is a generator of the entire group? We can check it here. 2 actually is only generating a small subgroup. Okay, 3, 6, and 9, 12, and 13 elements. Okay, of course 13 divides 42, therefore it is meaningful here. So 2 is actually generating a small subgroup, and I can also show you 2 is not a quadratic residue by just cutting the second column and showing you number 2 will not occur in this table. Okay, so let me do like this little command line hack. So what I'm going to do is I will just do echo, because my program needs an input. I will do 43 and pipe it to Python, and then I will be just doing some awk to print the second column, right? Sort it numerically in descending order. I'll show you the unique values. Okay, I think I made a mistake. Sort numerically. So you can see that number 2 is not even occurring as part of the second column. Forget about that A is not a number, it's just because of the new line coming somewhere. So as we can see, we took the second column in the generated table. Number 2 is not part of this table, this particular list of numbers that you're seeing. That means your number 2 is not a quadratic residue. And we also saw earlier from this output, what is 2 doing here? 2 is generating only a small subgroup. Okay, that's because number 43 is not a safe prime, right? 43 is 2 times 21 plus 1, and 21 is not a prime. Therefore, this theorem is actually applied in, the theorem must be applied in a careful way. Okay, logical flow must be correct. So all it tells us is that if P is congruent to plus or minus 1 mod 8, we can conclude whether 2 is a quadratic residue or not. Okay, it doesn't say anything about whether 2 is a generator or not. If P is not a safe prime, okay, that's something we need to be careful about. Okay, this is an interesting situation here. Actually, mathematicians have studied the quadratic residue for many years, and earlier we were asking, given a number, can it be a quadratic residue? They were asking a reverse question actually. For what set of primes can this number be a quadratic residue? So what they did is essentially prepared some kind of a table and then apply induction to draw general patterns, right? So they have, for example, here listed numbers from 1 to 25, computed the n square, and then computed mod n of n square, right? N square mod n. In this case, mod 3, not n square mod n square mod 3, 5, 7, and so on. These are all prime numbers, 3, 5, 7, 13, 11, all these numbers are prime numbers. So using this table, now we can ask interesting questions. Can number 2 be a quadratic residue when you are working with a prime P equal to 5? We can just look at this table and just see whether number 2 occurs anywhere. If it is not, we can conclude 2 is not a quadratic residue for prime P equal to 5. On the other hand, we can see it is true here, right? The number 2 occurs here. Of course, 2 can be written as a quadratic residue because as we can see here is 9, right? What is 9 mod 7? 9 mod 7 is 2. Okay, what is 9? 9 itself is 3 square. Okay, so using this table, we can draw some interesting conclusions. And Gauss actually developed many interesting theorems on quadratic residue. So I have this Gauss's book. Gauss is one of the greatest grandfathers of math, or greatest masters of math. He invented all of these many of the beautiful theorems that we are leveraging today. Anyway, so the conclusion is simple, that this is the foundation for many of the OpenSSL and boring SSL checks. And I have explained to you how this 24 magic number is actually interpreted using this particular theorem. All right, that's all, and thank you very much for your attention.